Just like I said, name is Yuri Vasin, and I'm doing reverse engineering. Like, shall I say that, I've actually been reversing so many different devices from x86 architecture to lots of others. I've been reverse engineering various embedded devices. Even reverse engineered electric kettles. So this will be a two-part presentation. One part will be about my personal experience, and I will also be talking about other people doing reverse engineering, various types of hardware and the kind of challenges they run into on a daily basis. Well, the second part will be kind of relatively new. I will be talking about hardware encryption modules that have never been played with before. So first, I need to present what I will be talking about. I will be talking about embedded systems. In fact, the way I see it is that an embedded system is pretty much any device or any system that's running on firmware. And I want to draw a line here between reverse engineering, let's say a Linux binary set can be running on your PC or a web camera or a web service. And on the other hand, the kind of research I'm doing, which is more bare bones, so to speak. What I'm trying to say is that I'm trying to research the part which is hardware dependent. It exists around the circuitry or for the firmware, naturally. So you can attack the same web camera as a pen tester or as a reverse engineer or as a researcher of the hardware. And these are obviously different avenues of investigation. I do believe that a breadth of experience really matters. You don't really need to have all this experience in your own, at your own fingertips. You can rely on the knowledge of the people you know. But, this industry is developing so fast, and embedded systems are getting much more complex with every passing year. Take, for example, the circuitry of an iPhone. It has become already very complex. So, you can no longer do some basic soldering around it. And microprocessors are already extremely complex. Moreover, most circuits will contain more than one crystals that will have there will be several circuits inside, and each of them will have several crystals. So that does require a lot of knowledge. Take a pretty simplistic thing we did once when we tried to learn the password that was sent to a flash card. So we had to develop an extension board for all the connections, and we needed to read the specs for the card in order to be able to parse the data for the password extraction. Now I'm going to tell a bit more. On-chip hardware devices, usually when people publish photos of crystals or chips on Twitter, they will identify different elements like flash memory and RAM memory. And you will often see a module called the periphery. And periphery or peripherals is not just a single device, right? It's a collection of various units that usually make your device run faster, but also make the life of a developer easier. So I'm here to tell you what these peripherals are like and what you gotta keep in mind when you're dealing with them. So this is an IDE screenshot. What do they have in common? The parts on the left and the right both are obviously division functions, and they both pertain to microcontroller 8051. You will notice that it's 88-bit architecture, which is not very common now, though this particular architecture is relatively popular. So often you need to divide functions like 32 functions or 64. And as a software developer, You obviously can rely on code to do that for you, but that will require a lot of memory. So you see pretty much the same code on the right, but it's done by the hardware, not the software. And this way, your controller will be running much faster. The same example with the memcopy function. So you can copy memory string by string or byte by byte. And that will take a lot of time. But if you take embedded systems, most of them are strapped for resources, and you may want to do fancy things with them, like sound processing or video processing. So simple copying of data from, say, A to B will require hardware copying modules.
Может быть погнут разработчиками. Что может быть вообще этими устройствами? Теперь вот это пример ширпотребного такого.
What kind of devices can we find there? I'll take, for example, STM32, which is a mass market device. And all you see here is a bunch of peripherals, actually. You don't need to rely on all of them for your development. Moreover, if you're doing, say, reverse engineering, you're not guaranteed to run into all of them. But say there is the JBIO module that helps you manage the power, the controller lag, and so on and so forth. There will be, for example, modules doing checksum calculations or data decryption, and doing all this stuff with software would have been inopportune, let's put it like this. Or take, for example, a flash memory controller here. You know, the core, the kernel, obviously needs to store data and record data, write data to its memory. That requires a hardware module that will be used by default, and people don't even stop to think about it. I've already mentioned the complexity of these devices has been growing by leaps and bounds. Take, for example, AVRs and versus ARMs. You know, datasheets for one of these groups is like 200 pages long, so in order to blink your LED, for example, you will need to read all these pages. In order to do the same on STM32F7, you will need to wrap your mind around 10 registers, and the data sheets can be quite scary, being 3,200 pages long. So I'm trying to explain it here using some recent examples from the market. But the point I'm trying to convey is that reverse engineering is primarily about discovering the logic of these devices, usually without having recourse to data sheets. So, for example, a video camera will have, its own SoC, and like a couple of vendors will be using this SoC, but others won't. So you will need to read the separate specs for it. So if you need to simply put data into AR interface in a disassembler or a decompiler, you can see, what's happening at the register level where most of the fields will be occupied, and you will have to stop the bits inside this registry many times, but you still will struggle to learn what these particular bits are doing.
Следующий посыл, который мне хотелось бы прям донести, что важно, что обычные вещи embedded системы, казалось бы, крайне простые. Они вот на вид простые.
Another important message I have is that embedded systems appear to be simplistic, like a couple of circuit boards, a flash controller, but in fact, it is an illusion. They are, in fact, quite complex. In the functional layout, you will discover that there are USB controllers of a USB card, a NAND flash controller, DMA engine, RAM and ROM, and MCU, lots of things packaged into this pretty slim format. So if you're going to research embedded devices, and you haven't been given the source code for them, but you're doing a kind of a blind study, well, there will be a lot for you to work with. Again, people don't tend to think much about it, but even dealing with the regular NAND memory will require a lot of time spent, say, in preparation, because you need to assure that lots and lots of functions are indeed supported. So I'm showing some of the functions you can find in an NAND flash controller. So I've broken it down into two groups, showing what the flash controller itself is responsible for versus the functions of the CPU. Take, for example, wear leveling. Well, you wouldn't really want to write the same page down many times because of the wear issue. And there are special algorithms for wear leveling. So even if you're writing the same information down, this information will be written into new memory blocks, and there will be a special algorithm for remove later and garbage collection.
Он будет собирать и по-настоящему очищать эти блоки, то есть записывать туда нули. Потому что операция, например,
And eventually this older information will be replaced with zeros. It will take time because it's pretty much a long process. Moreover, in your microprocessor kernel, you will also need to support flash conversion layer, flash translation layer, I'm sorry. So you need to convert addresses into real physical ones. And NAND is by far non-linear because it's composed of units of blocks, and blocks of pages, and pages of chunks. Moreover, units can be put together to form abstractions. So you need to store all this information in table form, I assume, somewhere in the memory. So what does the flash controller do? That's the hardware module that doesn't really depend on the programmer. So as a developer, you should be able to set it up easily. Like I said, memory is prone to degradation, so bit errors can easily appear, can easily emerge. Correction codes can obviously help you. So during the reading process, the flash controller can identify errors, and then as a software developer, you will be able to read the right data from NAND directly. But sometimes when you have too many errors, the microkernel will mark a particular block up as a bad one, and it will never write new data into it again. And I think this is why the size of flash drives goes down over time. Also, your flash controller needs to support different NAND modes, because the size of crystals doesn't grow. What does grow is the amount of data stored in a single cell. For NAND, a cell is a transistor with an insulator valve. There, you can store data in SLC mode, and it's pretty simple. Like it's either there is no charge there, or there is a charge of 3 volts. In MLC mode, you can store 4 bits instead of 2 bits, but that would require 4 different levels of charge from 0 to 3 volts. Which means that your NAND controller needs to know how to translate charge into digital data. There is also a scrambling feature there, designed to make sure that, say, for example, you're writing down lots of zeros, which is bad for your NAND memory. That's why all the data going into NAND tends to be scrambled by doing XOR sequence on top of your real data, thus creating a lot of white noise. I hope I have been able to convey the idea that even a simple USB drive is not that simple. So imagine that you need to reverse engineer a USB drive and maybe add some extra functions to it. You may have, a very concise data sheet or maybe nothing at all. And you would want to read a particular element of memory or run a search across the whole NAND memory. Or maybe you want all the data coming over USB to be written into NAND in an encrypted manner, or maybe having some XOR sequence overlaid on top of it. Then you can go back to the functional schematic in order to learn what you actually need to reverse engineer. So obviously, you'll need to wrap your mind around the USB controller. Say, if it's a USB 2.0 drive, which is quite complex already, but USB 3.0 controller will be colossally challenging. So you will need to rely on your intuition that, okay, maybe data has already arrived, and then you see in the firmware that some data is being processed. And then in a different hardware register, you will see another bit, emerging. And then you convert data from USB controller to NAND controller. So as a software developer, you may discover you're not dealing with data at all. You will be too busy setting up various controllers with your bits. In all probability, you will find it very difficult to spoof or replace data as such there. So if you decide you want to spoof the data there, you will need to play with the DMA controller and learn what kind of arguments it's using. I've already mentioned something about NAND controller. Take DMA, for example. With DMA, you can mostly see it, right, because of the memcopy function. And you'll see some arguments such as SRC and receiver and size or volume, maybe some other simple settings. But NAND controller is in a different league of complexity because there are lots and lots of functions which are embedded in the hardware, and you don't really see them happening at the software level. Which means that if you want to reverse engineer a USB drive, you actually need to learn a lot about NAND and how it operates, because otherwise you won't know about SLC, MLC, and QLC modes. Maybe you aren't even thinking that in order to do proper reading from NAND, you need to set the right mode. In the following example, I want to show that you gotta be prepared for the unexpected. I mean, you can never be prepared for everything, but you can try at least. So that's a simple example coming from my colleague called Nikita. So he was doing a simple USB NVMe, and we're trying to see what was wrong with our test, because we knew how to send data to it with some simple commands, we knew how to read data off it, and it did have either a signature check mode or something else that we could not identify in the update utilities or the firmware. And then it turned out CRC32 of the whole firmware is calculated block by block, but it's done on the hardware level, not software level. Maybe because it's faster, maybe because it's architecture M8081, which supports so many numerous devices. So there was a bit added. And it's impossible to identify it. It can be 1, 2, 3, and as we're trying to update the firmware, we tried to read the RAM, and we discovered
Причем меняются
There
при
were some
работе каждого
minor changes happening every time a new block of firmware was being dispatched. So we decide, okay, must be 32-bit calculation happening there. And then another colleague of ours said that in this utility,
подсчета CRC.
he actually found a bit unusual polynomial for CRC calculation.
Во-вторых,
And this led us to this discovery that is CRC block by block in a weird order, and the CRC itself is a bit irregular.
каким-то вот эмпирическими, косвенными
So it was partially through intuition, it was partially through indirect conjectures that we have been able to crack it.
потому что
And these things you can hardly ever prepare for.
появляется подпись аппаратно, но это хотя бы подпись штатной RSA.
Because you know what, in most systems, even this most complex one, you'll see that signatures get checked, but they get checked in a particular manner. So if it's CRC, it's checked at the software level. If it's not, it's a hardware check.
Надеюсь,
But here you go.
сказать.
Now, when I hope you have already understood my gist, I will be talking about reverse engineering of microprocessor
Хотел донести вот в этой первой
hardware. I'm sorry, firmware.
опыт общения с людьми, коллегами, с знакомыми из отрасли, с проведенных собеседований. Это то, что вы должны относиться к задаче
Oh, there is another message I had.
намного шире. Вы постоянно должны
Philosophically speaking,
вашего именно исследования.
I posit that reverse engineering is an ever-expanding field. You know, whatever you're trying to reverse engineer, you will end up reading so much more. You will get to read manuals for your current circuit, but also its precursor circuit. And also, so many things you didn't even think about, such as simulators or emulators or what have you.
Которые взаимодействуют
You will end up
с embedded устройством.
learning a lot about software which interacts with this embedded device. It could be servers or other hardware, so you'll need to
Собственно говоря,
analyze the technical schemas as well.
нужно, потому что он будет там с битиком.
So you need to learn
Надо уметь,
interfaces, even simple ones like ORT,
требуется большое
which does some very simplistic checks.
написано дебаг, но это довольно широкое понятие, потому что сейчас
Now I state debug here in my slide. In most cases, that's JTAG, and it has very complicated and very long specs.
не
Interacting with these interfaces can be very difficult.
программатором ваш
In
контроль.
most cases, you cannot really rely on the standard issue utility for debugging.
Аппаратный модуль Keylog, который обнаружен был в
In the second part of my presentation, I want to talk about keylock, which we found in big controllers coming from a pretty popular vendor called Microchip.
исследовал я, то есть сам вообще алгоритм Keylog довольно популярен в
So
устройствах.
the keylock algorithm is pretty popular when it comes to remote locking devices. It could be garage doors or flat locks, or it could be
Радиомодуль
alarm systems for your car, whatever.
беспроводно по радиоинтерфейсу.
So there are two devices usually connected over a radio,
На самом деле, так,
and it may sound like I'm advertising something here, which I'm not.
Flipper, он как раз на тот момент только
I was initially thinking of using Flipper because when I started my study, Flipper was all the rage.
Но вообще,
So I decided, how about I sniff the radio frequencies with Flipper, and it provided some interesting results.
частоту, потому что Flipper
Because with Flipper, for example, you can identify the carrier frequency of, say, a simple remote control, because Flipper can do some simplistic spectrum analysis for you.
вы можете получить. Вы
I mean, it's not the real deal when it comes to spectrum analysis, but it's good for
можете определить,
a bunch of applications like identifying carrier frequency.
может быть, не
Also, it can help you identify signal modulation methods.
интернета, что в
And the picture here also shows
мегагерца модуль
that the frequency is 433 megahertz. It's doing amplitude modulation and a 64-bit keylock. So simply by clicking the keylock button several times next to a flipper, I was able to see that, Flipper can do quite a lot of discovery into keylock, which is not guaranteed, right? Flipper can support some devices, but not others. If this is the case for you, you can do keylock analyzer, and then rather than connecting to the antenna, you will want to connect to the transistor connected to the antenna. Now, a few words about keylock itself, something I didn't know before I started this project. So keylock is a block cipher, which actually relies on a register kind of transposition. It was developed back in 1980s, then was sold to Microchip in 1995. And it is used a lot now in HCS series. It's a full-fledged circuit you can put in your remote control, and it would send encrypted data, and it can send data over radio right away, but that will require attaching an antenna. I've already mentioned that it's used in various locking systems. So I have keylock, and I have the firmware for it. So what I see here is that the key length 64 bits, block length is 32 bits. The number of rounds, I guess it varies, but here we see the standard length of 528. So this way I should be able to look for arrays of the same size for some specific operations. That, however, I didn't find. Firmware for keylock is pretty short, so it was easy for me to identify these functions. Register 111 to 114, you see that you're sort of writing data there, and then you don't read anything out of there, but you write there again, which suggests that it must be some hardware entry. Moreover, you see that the value for reg 110 is 0. Moreover, extra data gets written into the same full registers. Then in the cycle, you'll see that bit 7 becomes bit 0 for registry 110. And when that happens, from the same data registers, 111 to 114, data does get read. Well, it does look like encryption to me. Moreover, it's keylock. So I'm wondering, maybe that's hardware-based encryption. So I started reading the specs. I was wondering, well, AES is often done software level. What about keylock? Is it there on software level as well? So I was looking for it, and I realized that there were 5 registers associated with keylock. So it's pretty easy to see what 2 bits do. So they choose mode of encryption versus decryption, and to start encryption. And it also says that in order to use keylock, you need microchip license. But that was all I could find in the how-to, so to speak, in the manual. So apparently developers of such remote controls buy those licenses in order to use those encryption modules in their devices. With a bit of research, I discovered there were 3 controllers from the same company. Sometimes they're called keylock modules, sometimes they're called cryptographic modules, but in fact, it's just the same module, really. And you can find the word keylock everywhere. So in order to learn how this device worked, you certainly needed to know something about automata, or, as a developer of embedded systems, you would have some understanding of modules like this. So a finite automaton or finite automata system usually works like this. You have a bunch of predetermined states, and transition between them can be time triggered, or external factor triggered.
Эти переходы все заранее определены между собой.
All these transitions are predetermined, like I said.
В другую точку.
So in order for you to go to, from one state to another, from, say, encrypted data to decrypted data, or the other way around, there is just a single journey you need to take. Although you may want to have several iterations there. And this is something I've seen many times in my life before. So I assume that registry 110 was registry control, and the bits there would probably be responsible for modes. So I was assuming that I had to enter the key and then feed the data, start the encryption process and then collect the encrypted data.
Реверсишь прошивку, читаешь про keylog, делаешь какие-то предположения.
So I was both reversing the firmware and reading up on keylog. So I assumed there would be 4 modes. Mode 0 when you're when you're writing data. Mode 1, magical. I don't know what it's doing, but it seems to be mandatory. And in this mode, byte 0x42 is written to the registry for reasons still unknown. And there are modes 2 and 3 responsible for writing 64-bit into key H.
Используя 4 регистра, в данном случае можете...
And the fourth one, which does what the table suggests. So using these 4 registers, you can write several elements of the key and do some magic stuff with the second mode, and then you can use the control bits to start the encryption process. Then you can check if encryption is over, and when it is, you can collect from the same registers where you put your plain text data, encrypted data. So I made this assumption, and I bought several big controllers and a programming device or encoding device, and I started writing some simple code to try to encrypting codes and comparing it to what, say, Python or other systems would code it like. And that turned out into a short library which is currently available on GitHub. I had to test it, I had to play
порядке записывать байты в эти 4 регистра.
I had to play with different sequence of writing bytes to these different registers, but finally I cracked it.
Часть моей деятельности и реверс это.
So this is part of what I do when I do reverse engineering of hardware and microprocessors. I hope you liked the presentation, and I feel like inviting you to join us and do reverse engineering of embedded systems with us. If you want to learn more about this subject, I'd like to point out that the corpus of knowledge is in fact limited. And a very common question is, where do I read up on reverse engineering, particularly for embedded systems? The thing is that there is no reliable textbook. There is certainly a library for keylog devices. There is also a great book over there. There is also a good Inside NAND Flash Memories book. You can find this book and discover that it's a huge book. It's like a Bible, and it talks all about flash memories at length. So you can certainly find links to various flip firmware, including Flipper Zero. There is also a link to a report which taught me a lot about sources. I've heard that a book on reverse engineering of embedded devices is being written right now, and it will be, I guess, one of the best sources of knowledge, books of knowledge on this particular subject. I'm not sure if it's gonna be available in Russian or in English. That puts later in my presentation. Thank you very much. If you have any questions, please shoot, by all means.
Насколько сильно усложняет реверс-инженеринг спиленный все, обозначения микросхем.
If all the data on the kind of circuitry we're looking at has been shaved off, does it really thwart reverse engineering?
Я скажу так, что с определенным
Let me
опытом
answer it like this. If you do have enough experience with circuitry,
даже если они спилены,
you will have a pretty good understanding of what individual chips should be responsible for. Say, if it's a car circuit, for example, there will be some camp conversion or translation system. So even if you remove or delete the name, that will still be obvious. With microcontrollers, well, you will end up reverse engineering something that's not documented, and that happens quite a lot in our line of work. I'm not saying it's easy, it's not, but we do it a lot.